Mr. Carroll here, looking at DC circuits, both series and parallel. We're going to start out with our resistor circuit as a series circuit. Now, a series circuit is defined as a continuous end-to-end connection of the resistors to a DC power source. Here's your DC power source on the left. You have this resistor connected end-to-end. As it goes through, like a hose, you just add another piece of hose. You add another piece of hose. The same thing would happen here. Traditionally, the current flows from the positive to the negative terminal. As you see this red arrow coming from positive to negative. Notice in the sequence I've labeled them R1, R2, and R3 to keep them in order. The resistance R to the current flow, which is classified as I, is given in ohms. And the DC voltage, V, is in volts, where the current is in amps. The relationship between these three things are given as Ohm's law, V equals IR. Now, the first objective in the description of a circuit is to find the total current flowing in the circuit. Then we find its power. This requires us to find the total resistance inside the circuit. The total resistance is found by adding up these resistors. So you take R1 and R2 and R3 and you add them up. And in this case, it's pretty simple. You just get 150 ohms. Next, we apply Ohm's law, V equals IR. And since we're looking for current, it's V divided by R. So it's pretty straightforward. 12 volts divided by 150 ohms gives us 0.08 amps. Now, the power consumed is given by the formula power, P equals voltage times current. There's another formula, I squared R, that we could use, but in this case, it's very straightforward. Since we're given the voltage, we're given the current, and we find out that our power consumption is 0.96 watts. Now, once we find the total current flowing through each resistor, we can find the voltage drop across each resistor. So there's 12 volts from here to here. So if I go all the way around the circuit, I lose 12 volts. Well, how many volts do I lose in each one of my resistors? So we repeat this process for each resistor using Ohm's law. It's just V equals IR. So the voltage that I lose for R1, you notice the little 1 right here, is you take the current flowing through the resistor times its resistance, and we get 4 volts. Volt 2, or the voltage drop over R2, same current, different resistance of 4.8 volts. Then you get the voltage drop across R3 is same current, different resistance, 3.2 volts. Now, if you add these up, that's 12 volts. Now, the power consumption for each resistor, we just take the voltage that we get from here times the current. Volts times current gives us power, 0.32 watts. For this second resistor right here is 0.384 and 0.256 for the third one. If you add those up, you find it's exactly the same as it was before for our power consumption for the entire circuit. Now, it's really important for you to see, in a series circuit, the current is constant, but the voltage changes based on the resistance. So the current flowing through this pipe right here is the same all the time. And then you have a voltage drop across each resistor. It's really important for you to remember. Now, what do I do with parallel circuits? Now, parallel circuits look a little different. Parallel circuits are defined as 2 or more resistors that are connected to a single conductor. So if we take a look, here's the conductor coming in, goes across the top, and you have these things that literally drawn in parallel, just like you would in mathematics. And you have a conductor coming across the bottom back here. So the current will flow through each of these resistors. Now, it makes sense that the more resistance that you have, the less current flow that you would have. And if you thought that, then you are exactly right. But with the first objective in defining all of these things is, in the description of this circuit, is to find the total current flowing in the circuit, then the total power, just like we did before. But for a parallel circuit, we have a slightly different formula. We have a formula of 1 over the total resistance is 1 over R1 plus 1 over R2 plus 1 over R3. And if you look at this, it says, well, that's just the same thing, just flipped over. In mathematics, it doesn't quite work that way. So what we end up with is 1 over the total resistance is 1 over the first resistor here, plus 1 over the second resistor, plus 1 over the third resistor. If you work this out with a least common denominator of 600, you get 37 over 600, but that's 1 over RT, so we flip both sides over now, and we get 600 over 37, or 6.22 ohms. Now, if you remember in the series circuit with the same resistors, we had 150 ohms, so this is much less resistant. We can redraw this now as a parallel circuit. So if you take a look over here, instead of 3 of them, we now have 1 resistor with 16.22 ohms sitting right here. And because of that, we can now find the current that is flowing in this wire headed toward the parallel circuit with just Ohm's law. And we find out that it's 12 volts divided by 16.22 ohms, or 0.740 amps. Now in the series circuit, the total current was 0.08 amps. So this has significantly more current, and you will find also, because of that, the power consumption is significantly more as well. And so you'll find that the power is 12 volts times the 0.74, and you get 8.88 watts instead of 0.96 watts in the series circuit. Now you notice down at the bottom, note, significantly more power is consumed in a parallel circuit. Now that's if you want that. So that's in the design of a parallel and series circuit. You choose what you want as far as power consumption and in voltage and in current. So now we have the totals. So how do we calculate the voltage, current, and power for each of these resistors? Well, in a parallel circuit, the voltage is constant, but the current changes. Now in a series circuit, the voltage changes and the current is constant. So they're inverses of each other. And because of this, we know that the voltage here is always going to be 12 volts. And so that makes finding the current very straightforward. 12 volts divided by 50 ohms gives us 0.24 amps. 12 volts divided by 60 ohms, 0.2 amps. And 12 volts divided by 40 ohms, 0.3 amps. Now you notice the one that has the most current flowing has the least resistance. The most current comes from the least resistance of the 3. If we were looking for power consumption, you probably could predict that you'll end up with the most power consumption with the most current that flows through that resistor. Now, if you take a look at parallel and series circuits, they look different. In the parallel circuit, you have a single conductor with 3 or however many resistors that you have in your circuit and connected to another conductor. Over here you have a single conductor running end to end. So in the parallel circuit, as a review, voltage is constant, current changes, more power is consumed. In the series circuit, the current is constant, the voltage changes, and there's less power consumed. I hope you find this helpful.